Okay, thank you, Joseph, for this introduction. I think my part here in this tutorial, the second part, is going to be the longest. So I don't want to do it too much like me talking for 45, 50 minutes. So please, somebody interrupt me at some point during the presentation, please. And also, I want to talk a little bit about this schema that Joseph mentioned in the introduction, how we are just envisioning right now the data structure that simulations should have, and how you can actually use this for your own benefit. And of course, this is also part of the whole team of Area C, so not only me, but Joseph, Nathan, and Bernadette are contributing heavily to this new schema. And during this presentation, I'm gonna also swap from time to time to the terminal. And just, again, also because I don't want to only show slides, it's better if we maybe want to do some hands-on. But for this, I would just say like, okay, if because we are gonna pip install like the package. So if it doesn't work, then don't worry, just skip this part and then just look at what I'm doing. If it is working, then very nice. Then just try out with me at the same time, and you can also ask questions during this kind of play of hands-on that I'm going to show you. But the problem is like there might be like out of control problems with the Python versions that maybe you have in your computers, or maybe something internal that we cannot control very well. And okay, so that's it. Then I will just tell you a little bit the schedule. So it's going to be mainly about where this kind of a schema, so where all the definitions and the data model that I'm going to talk about is living. So it's GitHub, and I'm going to tell you a little bit about it. Then I'm going to tell you about the main concept, which is this section called simulation, and also what are the subsections or sub concepts or terms that are under that, now, which are these. Mainly this idea of the program, model method, model system, and others. But I mean, I will really go into details here and can get complex. And I think actually that we can make a break before talking about this model system part. So we finish this model method and numerical settings. And I think before talking about the model system, then we do a small break. I think this will be because model system is more complicated and will take a bit of time probably. So let me just introduce the repository. You can basically find this in this GitHub repository. It's called NOMAD-Simulations. So if you go to there, then, well, apart from being a PyPy package, so you can pip install this locally in your computers. There's a bunch of things. And here it's pretty much depending on how much you want to contribute or to give feedback, but we welcome anything, okay? So if you want to open an issue because, I don't know, you have been developing a plugin and then you think that one of these sections or data models that you have is better than what is currently there or more flexible, then we are pretty much welcome to it. And we are welcome, and we are happy when people just come to this GitHub repo and then they give feedback and anything that is considered there. So what you can find there, first, always recommend to read in any repo the README that you can see there, and just go over there is some documentation page. Although we are still under construction, and you can see it's like a very, very small version right now, so it's 0.02, so we are still in pre-alpha kind of style. And then you see a bunch of files, but okay, let me just pass to the next one. This is just a folder, so the files structure of this repo. And the important one is actually what is happening under this SRC, this source folder. And if you follow the tree, then you will see that everything is defined under these schema packages. Okay. And I'm showing you this because Nathan later is going to tell you how you can create a plugin for a parser. And the idea is that the structure is essentially the same. So we are in Nomad, we are all the time talking about plugins, because we are transitioning to this new structure. And the structure is going to be always the same. So when Nathan shows you how to create a parser plugin, he's going to add also like the possibility of extending the schema. And that means that you will also have this subfolder. And beside this subfolder, you will also have another folder for the parsers part. And here, I mean, the structure looks a bit complicated, but from you is not that much. There is like the entry point. But again, I'm just referring to Nathan to talk a little bit about this. But for us, the important one is that there is like more like the entrance. So the main definitions are happening in this general. So the main simulation section that I told you in the schedule part is happening here. And then we have like other definitions related with inputs, like this model method and model system, and I will tell you about in the next part of the slides. And then we have a bunch of things related with the outputs of a simulation. Okay, again, I'm going to talk about this at the very end. Everything else is just documentation, unit testing, and package releasing, and all the stuff that is not relevant right now. Okay, so let's go to the main section simulation part. But before that, because I don't have it installed in my terminal, I just want to demonstrate that indeed you can do it. I'm going to come to the terminal, and I'm going to just follow the instructions that we posted in the Discord and in the email. Okay. I'm sorry. Before I forget, I don't want to forget that actually you can go to the tutorial documentation page that we prepared, and that you can find all the explanations that I'm going to tell you now. You can find them here. And apart from that, there is these very nice assignments. So there's in this part 2, there are up to 8 assignments that will help you to understand how to populate this model and how you can follow these FAIR kind of principles like as we are doing. Okay, and it is an assignment, and then it has a solution in case you want to do it. And we are gonna do these, some of them through this part, and that's why I'm opening the terminal right now, because I want to first create a folder in which I'm gonna work. Everybody can see this, no? Nobody has any problem looking at this.
We can see it, Chema. Thank you.
Okay, very good. Then what I'm going to do first is just create a virtual environment. Okay, it has to be with Python 3.9. But yesterday I was testing, and you can also use other Python versions. The thing is that Nomad only, so the Nomad Lab package. So we are talking about Nomad simulations, but we also have the Nomad Lab core package, right? And that one works with 3.9. Again, for the functionalities I was trying yesterday, 3.10 and 3.11 were working nice, so maybe it's not that relevant. And I'm just gonna call this virtual environment whatever. And what I'm gonna do after the creation, I'm just gonna activate it. I mean, this is nothing but activating, and I'm gonna make sure that pip is upgraded to the last version. And here I'm going to tell you one trick. There is this very nice package that one developer from FAIRmat told me about, this UV. This is really making a difference when you want to pip install a lot of dependencies in your project. You just have to put, instead of just doing pip install whatever, then you put UV at the beginning, and it's way faster. And now what I'm going to do is just copy paste I have to put UV at the beginning. Copy paste the scripts, or no, sorry, the command that I said before, and then you will see fast pip installing. With this, well, this pip installing build, we can just go back to explaining about the sections, how these are written in Python, and how you can instantiate and populate these things. Okay, so now simulation and the main section. And here, I just want to tell you that, although I'm not going to enter in details about taxonomies and ontologies and the development of these semantic concepts, I just want to tell you that this is something important from the data management perspective. And you have heard before from Joseph about this interoperability concept and how you can have different levels. No? You can have like a very plain, simple data model, or you can also put this into some kind of expert or semantic knowledge that is out there. This is like more towards defining ontologies and linking between them. For us, what is interesting is that we have these systems to link with certain ontologies, and to even have like identifiers and so on. But for me, it's important to see that we have these two kind of very abstract concepts, which is called activity and entity. And this is the two concepts or classes in the Python sense that we use across all areas in FAIRmat, okay, both the experimental and the computational part. And it's just a class, and then there is in this kind of diagrams that I'm going to show you, there's always like an arrow with a white head pointing to somewhere else, and that means inheriting from, okay, which loosely speaking means normally that a concept is another concept, okay? And in the Python sense, it means that you have a class, and then you define that class, and then it's inheriting from that other class. In this example, for example, activity is inheriting from base section, and it's inheriting all the attributes and all the functions that I defined above. And you can overwrite them, and then you can reuse them, and so on. And the idea is that our simulation, or in this case, base simulation, I'm going to come why it's called base in a second, is actually living in this, so it's an activity, and it's living next to other activities in material science and chemistry, such as this experiment or measurement, and even analysis. Okay. And the idea is that under this simulation, so what are we going to have? We want to parse or put the data coming from simulations, and then we want to divide kind of like what is an input from what is an output in kind of these okay, I always have like these workflows kind of picture of handling data, as you're gonna see in the last part if we have time. So what we have is like a set of sections or subsections that are gonna live under our main concept called simulation. And we divide these in between inputs, which are this model system and model method, and then outputs, which is outputs. And then we also want to encode some information about the program that we are using. The name model just comes because in simulation we have we have to simulate ideal cases most of the time, right? I guess that all experimental people will agree with this, and then some computational people will disagree kind of with this naming. But it is what it is. It's just that when then we inherit, we can just put it at the same level as experimental people has their own systems. Okay, it's a bit defined. Okay, so how this looks in practice, it means that whenever you put data into a database such as NOMAD, then you will generate an entry related with that data. No, let's say a DFT calculation. And under that, what you will see is like this kind of tree structure of sections and subsections nested inside, which is nothing but a dictionary of keys and values, which can be nested inside of each other. So when you see like an entry archive, then you will see a main section called data, which is a simulation, is our activity, but it can also be an experiment, measurement, an entity, other stuff. And then inside that, we will have like 4 main subsections: program, model system, model method, and outputs. Okay. Here, one detail is that actually subsections can be repeated or not, in the sense that they can be a list or can be a single element. That's why a program in this case is just a single element, so we don't have a repeated list of programs associated with simulation and entry. But we can have a repeated list of model system, probably referring to, like, for example, the evolution of a geometry optimization, or some steps that were simulated through some molecular dynamics simulation, right? And consequently, we also have we can have lists of model methods and also the list of outputs. These you can also visualize. Oh, okay. And these you can add, the key of this is that you can access this information in this dictionary by just transversing until whatever you want to obtain. No? In this case, you go to the entry archive or whatever DFT or excited states or molecular dynamics entry. Then you go to data, to outputs, take the first element, and then you go to the electronic binder, and then you get the value or whatever the information you want. And you can also visualize this as a tree in these relations. So yeah, so before we jump, I think, well, okay, let's go first to these UML diagrams. And here, this is what I'm going to use very heavily. So I tried to introduce before like this kind of diagram where I pointed with these arrows taken from and stuff like that. But in reality, I'm going to show you things that are much more detailed. And okay, without losing too much, just think, if you like to think about this Python way, maybe it's easier. It's just kind of these boxes with these 3 pieces. Just refer to the class. So the name of the class that you have, then the attributes that you are defining for that class, and the methods or class functions that you have defined for that class. And I'm going to also change a little bit vocabulary. In NOMAD, we mainly refer to classes as sections, and to attributes mainly is quantities, although there is also this other option in a definition. If this attribute doesn't change during parsing, it's a definition, and if it changes during parsing, it's a quantity. But I'm going to use quantities all the time. And then we have this arrow that I told you about, this inheriting from, that we also have these 2 arrows, which essentially mean like when you have a subsection inside of another section, no? So a subclass inside of another class. So if you remember, like, for example, program is a subsection of simulation. there will be this box program, and then it will be connected with these arrows towards simulation. I will show you in the next slide. Both of them, they refer that. The only difference between contained in and reference to is that sometimes you don't want to repeat the information, so then it's useful just to reference to another part of the dictionary tree, the tree of sections that you have defined, instead of repeating again the data. So it's more like an optimization thing. Okay, so then if you want to zoom in what a base simulation is, then you will find these kind of quantities, which basically you will see the name of the attributes of these quantities and also the type. That can be either a datetime type or a float, and sometimes also I show like seconds. I mean, this depends. It's just how much you want to go into details, but that's more or less the information that is condensed there. And then when you see like a bold name, is mainly referring to a subsection living inside. So in the next slide, when I talk about program, you will see it probably better. And the idea is that we need to define this base simulation because we need to this intermediate point between what is an activity and what is our base class, because this class simulation needs to inherit also from another concept entry data. This is a detail of the Nomad software. It's just that later when we are creating entry archives, then we need to append the simulation to data, to the subsection data. Now, if you remember the lesson, it's just a detail. You can just because of this inheritance, it's just inheriting all the quantities. Then you can just forget about this and then only think about the fact that we have something called simulation, which has some quantities, and then it has these subsections called program, model, system, model, method, and outputs. Okay. And here there's another detail I'm going to comment, but before that, I just want to pass very quickly to the simulation, to the terminal. Sorry, here actually it starts with. And what I'm going to show you is actually how you can instantiate one of these sections. In this case, it's going to be simulation, and how you can populate some information there. I mean, it's going to be very dummy, but it's better to go slow. So I'm embedding this interactive Python terminal, and I'm going to do it here. And for that, what I need to do is to import the classes, the class or the section that I want to use. In this case, it is living in NOMAD-Simulations, schema packages, and is under the module called general. Okay. And then I just import the simulation section of class. And what I'm going to do is just instantiate that and then assign some attribute to that. I mean, if you know Python, this is really trivial. It just gets complicated later on in the video. So this is also part of the assignments of the first assignment in the documentation page. If you want to take a look. Anyway, I'm just going to assign a name. I'm just going to say that I did some BASC, DFT calculation, and I don't know, I'm going to say for some material like an assignment. Really, this name is kind of a bit irrelevant. It doesn't mean too much. The important things are quantities that are floats and strings that allows to identify the information of the metadata. And if now you want to access this simulation, then you will see that you have a class instantiated with a name. And then you can access the name, which is a string, and work with that. Okay, so very stupid, but it will help us later on, I promise. Okay, now let's go. Okay, I wanted to talk a little bit about the functions defined here on the last part of these boxes. And there you're always going to find this function called normalize. And the idea of this normalize function is that later when Nathan shows you about parsing data from input and output files of your codes, then you will see that, okay, it's populating. Maybe you can use some of these functions that are defined for the classes for helping you through the parsing process. But then after the parsing is finished, then the idea is that these normalized functions of all the classes will be executed afterwards. So these functions actually are very useful when you want to kind of take the burden of the parser. So there are all these operations that maybe are too abstract, so that they are not very specific to one parser, and that they can be used across. And that's actually, if you think about it, that's the kind of idea between interoperability. Like we want these kind of operations that harmonize the data between different sources to be living in the same place. And that's why the normalize function takes that responsibility for itself. And what means is like essentially for all the classes that are defined in this schema, there is always like a normalized function that has some operations or some logic happening inside. From very stupid things about just setting some names or some strings up to really like setting the same energy reference for the density of states or the band structure, for example, or extracting the band gap from a density of states if there is some band gap at the Fermi level. Okay. Because if you think about that, that doesn't depend of the simulation code that you're using, but you can extract it from all the data of the sources. And if you go to the code, this is how it looks. You will see like these classes. I talked already about inheritance. In this case of simulation, we need this double inheritance, and that's why we need this intermediate thing. And then there's always like a description that we are trying to improve. And then you instantiate, so you can define these attributes that then you are going to populate later on. This part I'm going to skip. I'm just going to refer to José's part because he's going to really show you how to extend these and how you can define these quantities and these subsections and so on. Here, just note that we are defining a subsection, so that means another section inside simulation, and then it's repeating, so it can be a list, like I mentioned before. And then we have like a set of functions that again, it helps us like either implementing some more analysis or to normalization and then making everything harmonized across different sources. And yeah, again, this is the important one where you should just think about defining this normalized function when you really want to define something that it doesn't depend on the software that you are parsing, but actually it can be as general as it is. Okay, so now let's talk a little bit about the subsections. Let's go from more complicated to more, let's say, easy. Sorry, from easier to more complicated. And the first one is program. I guess this is very easy to understand. It's like a section, so a subsection of simulation which contains information about the code that you use. So that means that mainly it's going to be strings and information about the code like pass, quantum espresso, V2K, whatever. And also versioning, and you can specify more things. The UML diagram looks like this. Now, if you look on the left, this is the simulation, so the base simulation section. And if you see now, there is another of these boxes, which is an entity, actually a program, which is contained in it. Now, so that means that it's a subsection of that. In this case, program has information about the name, which is string, version, and other stuff. And this can be extended as well with more information. But this is this model, and of course the normalized. Now, what I want to show you is how you can actually define subsections inside sections. But it's really easy. You just have to assign the attribute that class. And for that, what I'm going to do is now let me just make a little bit of space. I'm just going to import the section program. It's also living under general, same as simulation. So I'm importing program, and I'm just gonna define, because we have a bus calculation, so let's just call it, they just instantiate this class, okay? And they just say that the name is bud. Let's just also assign some version like, I don't know, 4.0.0. Let's just take an example like that. And then it's just as simple as saying, okay, now my simulation class, which was this was the FT calculation for gallium arsenide. Now you just assign the attribute to whatever subsection it is. And if you now want to see what is under simulation, then you will see that now it appears like the program. And if you just keep transversing to the information, then you can get what is the version, what is the name, and etc. Here, this allows me to show you this thing of transversing, but also I wanted to tell you that once you define attributes of these classes, or quantities of these sections, they have a specific type and shape that is validated in the data model. So that means that if you want to pass the version to be now another thing that is not a string, then the system is going to complain. It's going to tell you, in this case, that the value 4 is of class integer, and the system is expected to be a string because that's what you defined before in the data model. So that's how it works. So you can only change this thing if you really want, if you are really passing a string. And so if now if we go to the simulation program version, you will see that we have overwritten the information of the version, and again, there are these validations that ensure that you have the same type and shape and everything. Is it easy? Let's go a bit more complicated into this model method and numerical settings. And okay, the idea here is that now I'm going to tell you about these three sections, right? This model method, model system, and outputs, and also the details under them, these numerical settings, atoms state, and physical properties. For that, you're starting by model method section. First is that this is so it contains input information, but which kind of input? It's mainly the mathematical model that you are solving. So the kind of approximations or models that you wanted to solve, the theory that you use, kind of like this, and then you can have a class inheriting from this. You will see in a second what I mean. It can also be contained, so you can essentially have like subterms coming for this model method. So I mean, just imagine if you have a Hamiltonian, you will typically have like this concept of like the kinetic energy, so the kinetic part and the potential part. No? So similarly here, you can do the same. You can have the total Hamiltonian approximation that you did with some whatever information or strings or identifiers you want. And then extra, you can also identify subterms under that. I say that this is useful when you are referencing because later, if you think about calculating, for example, contributions to the total energy, then you will need to know which a specific part of the Hamiltonian you are referring to. Okay, this is too much intel. I just want to mention that it's possible to do this. And then model method has a subsection defined inside, which is called numerical settings. And this precisely refers to the kind of parameters that you use for numerically solve that model. This can be from, like, for example, if you did like a self-consistent calculation and then you define like, okay, what is the threshold I have to consider for this quantity, this property to be converged. That kind of threshold should be like it's a subnumerical setting, and then we will use a class called a section called self-consistency, which is inheriting from this numerical setting. So you will see it now. It's also referring to algebraic basis that you're using and the mesh, the K, the reciprocal space so far. But if there are other numerical settings that are important, then we are happy also to extend this. Okay, so the diagram now is getting a bit more messy. But now, if you see on the left, you will see, again, a simulation is inherited from base simulation activity. And then we have defined a subsection called model method. And this model method has this concept of contributions. In order for that to work, what we need to do is kind of an abstraction app. So we need to find something like called base model, and then consider that these contributions are a subsection of that. Okay, this is too much detail, but that's why we need this abstract section called base model method. And if you see here, besides name, type, external reference, in case there is some reference you want to add, there is also the subsection called numerical settings. And here, this one I'm going to show you in the next slide. So now we are just going to try to focus on, okay, which kind of model methods or Hamiltonians or mathematical models we want to use for this. And the idea is that you will always inherit from this class here, model method. Okay, you can forget about this intermediate that is also not so clear that it's going to survive in the near future. But the idea is that then you will have different Hamiltonians or models that you solve inheriting from that model method class. And you can have density function. These are the ones that are implemented so far. There's this density functional theory. You can have tie binding models like either Vanier, extended, or Slater-Koster. You can have dynamical mean field theory. I'm skipping this because maybe also will not survive in the near future. And then you can also have like excited state methodologies like GW, and so on. And this is the idea now, because of this inheritance and the fact that there is a concept also called polymorphism, that means that even though we have defined model method to be a subsection of a class called model method, because all of these are also a model method, that means that we can append directly into our simulation. Okay, this looks, and then also they are inheriting this subsection called numerical settings. So then there are a lot of commonalities. But let me just show you before somebody gets a bit lost. Now what we are going to do is we are going to try to create a class with some DFT section in it, and then just say that, okay, this is an LDA DFT. And how we do that? hopefully you already know that you have to add this schema packages thing. And well, we have to import this from model method, from that is not anymore general, but the model method module. And then we import the class called DFT. And now what we are going to do is just going to instantiate that class, okay? And in this class, if you will see the model, if you will really go into the details, there is a quantity called Jacob's ladder, in which you can actually use for defining the LDA or GGA or whatever exchange correlation function approach you use. So in this case, we just use Jacob's ladder, and then we say, okay, it's an LDA. And if you see now DFT contains that information, so again, you can just see what is going on. Okay, now what we are going to do is, because this inheritance together with the polymorphism, that means that we can directly append this as a model method section under simulation. So we have model simulation, we have model method, and then we can directly assign it to our DFT class. And if we will have like another mathematical model section, then we can just append it directly. Now, this is going to complain. And it's going to complain because I have directly assigned the attribute model method to be DFT. But the problem is this definition is a subsection will repeat. So it's a list. And the way of handling this list of sections is by appending them. So in fact, we don't need to, I mean, there are two options. No, either you have to pass this as a list, okay, like with the brackets, or you can directly append, and that will also you just append the section. And now, if you see, actually, that's the error message that you can see. If you see now, our simulation class has a subsection which has per name program, but then it has a subsection called model method, which because of this inheritance and polymorphism, then it's a DFT class. And as you can see, then you can access that information of which kind of exchange correlation function that you use. And of course, there's like a lot of details here. We are also using, in the case of DFT, we are using also the libxc, so the library for exchange correlation functions developed. So with more details on it. So this Jacob's ladder is just like the easy way of recognizing LDA, GGA, PP, and hybrids and so on. And for other mathematicals, other method classes like DMFT, GW, maybe in the future force fields, molecular dynamics, for all of them, they will have their own quantities defined. And the idea is that here you can really use this. So the only concept that you have to use here is to inherit from model method and then to define your mathematical command model that you use. I'm just going to use an example because I say Jonas Schaap here next to me in the Zoom. So they are in his case they are using quantum Monte Carlo. So it should be as easy as defining class quantum Monte Carlo and inheriting from models and whatever other approximation. Okay, now let's hopefully this was not very complicated. Let's go back to this picture, and then let's go to the numerical settings, but the idea is pretty much the same. Now, instead of talking about okay, here we still have the model method, the base model method, and I'm going to talk about the details of these numerical settings. So now here, what we want to use it is just to define our own sections that are talking about numerical settings parameters that we use. And for that, right now, we have three main sections called self-consistency, basis set, and k-space. Self-consistency that I already told you, it stands for when you did like a self-consistent calculation to store certain information there, like the minimization algorithm that you use or the number of maximum iterations and other related quantities. Basis set, which right now is empty, but we want to re-implement things here related like with the basis set used during the calculation, either like plane waves or atomic orbitals or whatever it was used. And then the k-space, which tells you either about apart from the reciprocal lattice vectors, it tells you about either the k-mesh that you use, so how much you divided the mesh in the reciprocal space, or in case that you did like a structured calculation, so what was the line path that you use over the brilliance. And nicely here, I just want to comment that for me, this for people who knows a little bit about data quality, these two concepts of numerical settings and model method look to me a little bit like the concept of precision and accuracy when talking about data quality. Because accuracy, you are talking about what is the overall accuracy of the mathematical model that you solve, while numerical settings talks more about the precision of that simulation for that specific mathematical model. From this part, I'm going to tell you a little bit, keep telling you about these subsections that live under the simulation concept class. So we are going to keep talking about another type of input, and then last we are going to talk about outputs and how we can parse this information into our data model. Okay, so for model system, actually it's an input section, and in this case, what we want to put in this section is actually information related with the real space information of our system or material. These are mainly like positions in the cell or in the simulated cell of atoms, but it does not restrict only to that. It means in more general ways, like what is the real space information that we have. And for this, we have a very nice concept of this nesting model system over itself. So the idea here is that we want to also give the possibility of creating these hierarchical systems or material structures, same as you would do also like in material science, no? Like, you know that, for example, if you have like a heterostructure, then you can also divide it into the layers. And that's the whole idea, no? That we will have a main parent model system section with all the heterostructure information. And then inside of that, then we will have like subsections referring to each of the layers. And the idea is that the idea is so abstract that it can be used outside of simulation. So probably this thing will be moved at some point more into the abstract level of that also experimental people can use. But the idea is that, no, like this having these parent-child trees of systems, okay? And I'm probably not going to show you how to do it, but that's also what is behind and what will be behind powering this picture that Joseph showed you about this molecular dynamics solution with some protein inside. No, I will come to that just in just a second. And then we also have some other subsections living inside model system, things about the simulated cell, so the use simulated cell. Then we have information also about the states of the atoms and the orbitals used in that cell. And I didn't mention the other one, but there is also other subsections talking about the chemical formula, symmetries, and so on. Okay, so this diagram is much more complicated than the one before, and it's the most complicated, I must say. But basically, if you see on the left, again, you see simulation by simulation activity, and on the right, we're going to talk about our entity system, okay, in these kind of sections that are shared between experiment and simulation. There is this intermediate class that is going to be, again, what I said before, is going to be probably widely used by other people. And then that's where we are going to use to inherit from for our model system. And there are many more quantities defined here. You can just for now just put a focus only on the bolded ones. So the cell, the symmetry, the chemical formula. These are subsections that live under model system. But the important one, like I said, is this proxy model system. So by doing that, then we can nest model system over itself, and then we can create these trees, so these hierarchical trees of systems, okay? This is one of the examples with molecular dynamics. So you have the full simulation cell with all the atoms positions, and then you will use like these subsystems, so this proxy thing, to keep defining inside of this, in this kind of nested structure. That's the whole idea. And then we have this subsection, cell, symmetry, chemical formula. So cell, it is used for defining the simulated cell, but also the position of the entities that you're using. And it's inheriting from a concept called geometric space, but I think this is going to change in the near future, because we also want to give the possibility of not having a cell, but just like some other kind of other simulated systems. Okay, so probably the way of fixing it is just that instead of using cell as our subsection, we just have to define something above now this geometric space. But this too much detail. And just coming to the question by Jan, then there is there is this abstract concept of cell, no, that tells you about the lattice vectors and the simulated cell and the positions in that simulated cell. And then there is that the concept of atomic cell. And we want to separate that because we want this very specialized concept of atomic cell to specify what are the atoms sitting in each of those positions. By doing so, you can in principle do models instead of real materials with real chemical elements by just simply defining now another object which inherits from here. So it can be like a force field cell, it can be a lattice model cell, stuff like that. No? So in this case, we only have this example so far, but that's more or less the idea that we have in mind, and that we actually welcome feedback from people to tell us whether this is good or not, and so on. And then, well, okay, just coming back to atomic cell, the atomic cell has a subsection called atoms state, which tells you which chemical element is sitting in each of the positions of the cell. And you have information also about the orbitals there and about the charge of the atoms if there is one. And I'm going to tell you in the next slide about this. And we have also information about the chemical formula under model system. These are typical identifiers or strings just to put all the elements of a system together in a chemical formula, and it has different formats. And then we also have a section called symmetry, which is referring to there is some symmetry classification happening here in these functions, in this normalized function. But right now it's just only working with bulk systems. But the idea is just to extend on this and then probably make it better. So probably this section somehow will change or will work slightly different with feedback from people. It's also working only for non-magnetic systems, so nothing about magnetism in anything that I'm going to tell you about today. And yeah, so right now what I wanted to actually show you is, well, in the next slide first, I just want to show you the details of the atoms state, but I'm not going to tell you too much about it. I'm just going to say that, okay, you have this specialized concept of atomic cell. You have a subsection called atoms state, and here is where you specify things like the chemical symbol, the charge, and even information about which kind of orbitals are relevant for the system. Like, for example, in core holes, you have this idea that you create a hole in one of the core valence one of the core orbitals, and then also like you have information about the Haber interactions if you want. And this is too much detail, so you can just forget about it. What I want to show you is that you can actually use the functionalities in just a very, very simple example. In the documentation page that we prepared for you, there is a much more complicated example at the very end. I think it's the 2.8 or 2.7. In which you actually use one of the functionalities of the outputs to check if that output is self-consistently converged or not. And that means that the functionality actually goes to the numerical settings of the model method and then checks and compares and so on. So here I'm just going to show you a very, very dummy example. And for that, what I'm just going to show is that actually you can extract information. So by just passing a string that identifies the elements that are sitting in your atomic cell, that you can extract information about the atomic number. Okay, this is very kind of dummy. And the only problem for this is that I need to create a logger, which is for logging messages, info and warnings. I just copy paste this code that probably I will put also in the Discord in case somebody is following. Okay, you just have to copy paste that. And the idea is that we're now going to create this atoms state class. And then what we are going to do is just populate the chemical symbols with whatever symbols we want. And then we are going to see how by calling one of the functions, then we can resolve the atomic numbers of that. So for that, we just import from a module called atoms state. Okay, it's one of the modules that we're going to import from. And now what we're going to do is I'm just going to do a loop just for simplicity. I'm going to say that for symbol in some list of symbols, just do something. For that, I don't know. I'm just randomly saying I don't know, lantern, wolfram, and oxygen, no, and two oxygens sitting probably in two different positions in the simulated cell. And here, what I'm going to do, I just have to instantiate this class. Okay, I just have to associate the chemical symbol to whatever symbol we are passing. And wait, okay, sorry, because I forgot that we actually have to create a list, an empty list first. Then we can do this thing here. Sorry for that. Okay, and then we just we just append this state into the list that we create. Okay, so now we have an atoms list, which is the 4 atoms, no, lanthanum, wolfram, and oxygen. And then what we can do is just use this one of these methods. It's called resolve atomic number. We just have to pass this logger, and that's why I had to define it in order to get the atomic number of each of these chemical elements. And I'm just going to use list comprehension here just because it's easier. So I just say resolve. I just call for each of the elements in this list. So for each of these sections or classes, and then I'm just going to call for the method called resolve atomic number, and then we have to pass logger. Okay. If you do that, then you see like you actually obtain the atomic numbers of each of these chemical elements. But this is just a very dummy example, and again, there is an assignment which is much more involved, and I can only recommend you to check it out. Okay, and that's for model system. Here, there is not so much about inheritance. So I will argue that if you like the data model that we have here, then you use it. If not, either you have 2 options, no? Define whatever you want yourself, or try to help us like improving in this schema. No? So the more people give feedback specifically into this, the better it will become for people outside your own subfield, subcommunities. But again, there is not so much inheriting from model method and from numerical settings as it was before. This is more like kind of static kind of data model, to name it somehow. Okay, then last part, and with this I shut up, I promise. Then we are going to talk about the outputs, and for this we have the concept of a physical property, which is very important. And in this section, what we want to put is actually the information of simulated properties. And for that, we are going to have like our section, and then under that, we are going to have a lot of subsections defined. And each of these subsections that we're going to define is just associated with one of the properties that you can simulate. It can be band gap, band structure, density of state, Fermi levels, up to spectra data like Sorsen spectra or Green's function, stuff on Earth. And then the idea is that all these, because these are going to be classes, all of these classes are going to be inheriting from a kind of abstract concept called physical property. And inside of physical property, we have a subsection called variables. And this, if you remember about model method, that we have numerical settings, because of this inheritance and polymorphism, that makes that it's easy to just append things that are variables into things that are physical properties. It sounds a bit strange maybe in our face, but that's it. And the cool thing of this is that the idea is that this physical property abstract class and the variables class, so these 2 bullet points here, are actually pretty abstract to the point that it can also be used by experimental people. And in fact, in FAIRmat, there is a task force, so a group of people that is working towards creating a taxonomy of materials properties. And the main idea behind is to have like an interoperable, this kind of abstract concept, so that people either from experimental simulation can use it independently of what are the details of the method used to obtain that property. So when I talk about the band gap, I'm just referring to a band gap with a value, and that kind of class could be in principle populated by either by a simulation or by an experiment. Okay, and there are some details here about how a physical property is handling things, because this is a section which is actually having some attributes and some validations happening inside. I just don't want to talk too much about this because probably it's going to change also in the next weeks, months. But I just want to give you the brief idea of what we have in mind. So the idea is that you're going to have a physical property with the value of that physical property, like electronic band gap, and then the value is going to be whatever, electron volts or joules or whatever. Then there are a couple of other attributes which are going to help us to determine the shape of that value in a kind of a more dynamic way. So if you remember at the beginning in the first part, I told you that when you define a quantity, then it has a specific type and it has a specific shape. and there is some validations. And if you don't pass the correct type or shape, then Nomad will complain about it. But now what we want is to give more flexibility to this. And for doing so, the idea is to have this concept of variables that is going to allow you to define whether you have a function, which is a scalar, or which is just varying over some set of variables, okay? If you think about the band gap, for example, that could be like, okay, maybe you only want to store the band gap to be only like the scalar value of your simulation, but maybe you are also obtaining that in terms of the temperature, and then you want to store that as an array, right? And the way, I mean, there are two ways. So either you have to define two different classes, like band gap or temperature-dependent band gap, or you just try to do this kind of dynamical shape thingy and then try to go towards it. The first one is really bad, because that first option means that you have to do all the potential combinations of variables that can happen for a physical property. So okay, that's why we are going towards this. And then also some details about references and contributions to avoid overclassification. And again, going towards that line, we don't want to define things that are too fine details, but we are more interested about the abstract concept of a physical property and the most general concept of a physical property. So we don't want to define things like total density of states, atomically resolved density of states, orbitally resolved density of states, but we just want to define something like density of states and use it for us. And connecting a little bit with what I said at the beginning about having systems to connect with ontologies and this semantic development, then we also have in place some identifiers and descriptions which are going to be taken from this task force, this group of people that is working on defining properties from different fields, from different parts of experimental simulation. So we only have the responsibility of parsing and of adding more functionalities to this. And I'm going to come to that in maybe 1 second. So how does it look? This diagram is maybe too much detail. I'm just not going to come. You have a class called physical property, which has a subsection called variables. And here, just a small detail, variables can be also thought about to be like also physical property, but it's just a simplified version of that. Because for the physical property, we contain more information. For variables, we only want to see what is the grid of points, not that we use to vary that other physical property. That means that we have probably to repeat like a class that is inheriting from physical property. Sometimes we'll be also inheriting from variables. I will use it differently, like temperature, for example. That's the best example I can come up with. And then you will have all the physical properties like electronic band gap, Fermi levels, chemical potentials, etc., just inheriting from here and appearing as a flat list of subsections under outputs. So if you see, if you have simulation-based simulation, we have a subsection called outputs, and then we have a full list of subsections. So there is this kind of thing here. And all of them are related with things right now that you can simulate and you can obtain from simulations. And the idea is just to keep extending this long list to cover all the potential things that comes from this taxonomy task force. And all of them are inheriting from physical property. So just take a look on the arrow. So all of them are a physical property. And physical property has these variables again. And then you can also have like a list of variables that you can define, temperature, energy, frequency, whatever. Also K points, whatever they're using. Okay, and I think I'm going to skip these parts. There are also references, but it's a bit too much detail probably. But there is also like the concept of self-consistent output. And for this is used when you have a property that is self-consistently calculated, then you will use this class instead. Because it's inheriting, then you can use it as an output, but then it has also this additional SCF steps subsection, which allows you to add properties that are evolving in each step. And the assignment that I told you about using functions is more involved because it's using this resolve is self-consistent converge method here, and then it implies knowing a little bit more details on this.